Hey everyone, this is a walkthrough the Level 3 Physics 2023 Waves paper. Go through the Achieve Merit Excellence as you normally would. I'd get a pencil, rubber, calculator, and your equation sheet to hand if you haven't already. As ever, whenever I start a question, listen to me explain as much as you think you need help with. Then pause it, give it a go yourself, then have a little look at any bits you might have missed or where you might have gone wrong with my answer afterwards. Give it a go first though. Alrighty, question 1. Sam's violin. Assume that the speed of sound in air is 342 meters per second. Now we're told that a violin is a stringed instrument onto which the strings are fixed at both ends. The fixed points are 0.331 meters apart. Sam plays the violin, making the strings vibrate by pulling and pushing a bow across the strings. Okay, just underlining some key facts from there. One string, called the G, is arranged to play a fundamental frequency of 196 Hz. Calculate the speed of the wave that travels along the string. Now, we're given quite a lot here. We're told the speed of sound, we're told how far apart the points are, and we're told the frequency. Now, our wave speed equation is V equals F lambda. Now, we're told what the frequency is here, and because this is a fundamental frequency, it means that even though we're not told the wavelength, where we're told the length of the string, we can use that length to work out the wavelength. Now, if I just draw a quick sketch of this string, the fundamental frequency means it vibrates with this sort of wave pattern. It's a half wavelength, and it just vibrates up and down, a bit like a skipping rope. What that means is our length is half of the wave, because to complete this wave, I'd have to draw the same thing again coming up the other side. And so our wavelength is equal to 2 lots of the length, which is equal to 2 times 0.66. Oh, that's the answer. 0.331, sorry, equals 0.662 meters. Now our frequency is 196, so our velocity is just 0.662 multiplied by 196. And that gives us, I use a calculator, 129.752. As ever, write your unrounded answer and then your rounded answer. Okay. If you're ever going to round an answer, write the original one as well, just to be safe, particularly for show that questions. Okay. Now, part B says, analysis of the sound produced by the vibrating string shows that it also vibrates at 392 Hz and at 588 Hz. States the harmonic that causes the vibration at 588 Hz. Your answer should include a sketch that shows the location of the nodes and antinodes. Now, for any frequency we have, the number harmonic it is just how many multiples of that base fundamental frequency is. So my fundamental frequency equals 196 Hz. 588 divided by 196 gives me 3. So this is the third harmonic. And I've run out of space, shouldn't do that. It's the third harmonic, okay? So all the harmonic frequencies are just multiples of the fundamental. This is 3 lots of the fundamental, so that's our third harmonic. Now we are also going to include a drawing. And as with any of these drawings, we're talking about half wavelengths because we've got 2 closed ends. We're going to start with a node at either end. Now I know, because it's the third harmonic, there are going to be 3 lots of a half wavelength, so 3 half waves to fit. So I'm going to try my best to split this into 3, just really eyeballing it, not really measuring it out. Okay, Now, these are all going to be our nodes. Okay, all of those 4 points are going to be our nodes. We're then going to just fill in the gaps with a half wave between each of those nodes. Okay, easy as that. The last thing is just to label on your antinodes. Sorry, I should have said, for question 1, it was an achieved question just for the right answer. For the second one, this is a merit answer, and you had to have stated clearly that it was the third harmonic and have a labeled correct diagram. If you only did one of those things, then it's achieved. Okay, but it's easy as that. In between the nodes, wherever you've got peaks and troughs, they're your antinodes, your maxima, whereas your nodes are the stationary points on the standing wave. Okay. Now, part C, we are told that Sam plays her violin with a fundamental frequency of 196 Hz still, as she sits on a moving trailer. The trailer is moving at 5.3 meters per second, directly towards microphone A. So I'm going to start underlining stuff that I think is going to be important. We are then calculating the frequency recorded by microphone A. Now, microphone A is being driven towards by the trailer, which is going to be significant when we're choosing which sign in the equation for the Doppler effect. Because we've got a sound being generated on a moving platform, hopefully it's clear that we're thinking about the Doppler frequency, the Doppler effect. So I'm going to write down our equation before I do anything else. F primed is equal to the original frequency of the sound multiplied by the wave velocity divided by wave velocity. Now on your equation sheet here, it says plus or minus the wave speed. Sorry, the speed of the source. Sorry, not the wave speed, the speed of the source. W for wave, S for source. Now, if the object is if the observer is moving towards the sound that's being generated, then the distance between them is getting smaller. And so we can say that we're going to use the minus here. Now, if we were measuring the frequency at position B, then we'd use the plus because the distance between them is getting bigger, they're spreading apart. But because they're moving closer together, we're going to use our minus. And then we're going to put all our numbers in and hopefully calculate an answer. Now, our original frequency is 196, we're told that in the question, equals 196. Now we're multiplying that by the speed of the wave. Now this isn't the speed at which the wave moves along the violin string. We're talking about the speed at which the sound moves through the air. That's a little bit different to usual. Here, this paper, we're saying that the speed of sound is 342. So if you've memorized 343 over time, this paper is expecting you to use 342. This is a little bit of a curveball. I'm going to do 196 multiplied by 342 is the wave velocity, divided by 342 again for another VW, minus the speed of the source, which is 5.3. Minus 5.3 in the denominator. And if you're typing this in a calculator, make sure you use brackets so you don't confuse the calculator. You put all of that into it, and you should get an answer of 199 Hertz. Okay. Now, if you did all of that, got the right answer, that was a nice merit question. If you put the right numbers in the equation but made a mistake, it looks like you get achieved. But if you happen to use the speed of the wave traveling along the string, 130, instead of the speed of sound in air, then you were still given the achieve, even if you got the wrong answer as a result of that. The last part is the excellent part for this question. Microphone B is directly behind the moving trailer, whereas microphone A is directly in front of the moving trailer. Explain how the motion of the trailer with Sam sitting on it playing the violin affects the frequency of the string, the speed of the sound in the air, the wavelength of the sound in the air in front of and behind the violin, and the frequencies detected by microphones A and B. Now, this is an explain question, and it's given us 4 sorts of bullet pointy clues to help, but not a lot of space, only there's like 10 or so lines in which to write it. Now, first of all, when we are moving, if we're a moving object, and if you're moving with that object, you will notice that the speed or the frequency, the sound that you hear while moving with them does not change. Okay? Therefore, the frequency at which the string is vibrating doesn't change. Its impact on the air between you and it as a stationary observer does get affected, but the frequency of the actual string's vibrations are not affected. So we can say the following. The frequency of the string is not affected by motion. If you start playing guitar and start walking around the room, the sound emitted does not change. If you're moving quickly enough, somebody might hear a difference if they were staying still, but the strings themselves do not change. So we've done that one. And I suggest you go through and tick off each bullet point as you deal with them. Now, moving does not change the speed of sound. The speed of sound in air depends on the spacing of the air particles themselves, not on your motion through it. And so the speed of sound in air is independent of motion. Again, so these first 2 bullet points, they don't change basically. They're irrelevant. We have to say as much for the full answer. Now, because we're now talking about how the wavelength and frequencies are affected, we do need to be very thorough in our descriptions. They expect you to explain this from the ground up. So we're going to say, as the trailer moves forwards, it keeps emitting new sound waves. Okay? Now, Now, because we're just saying that as a nice general statement, because then we're going to describe why that's significant. So, as they're moving forwards, each wave is emitted slightly ahead of the last one. Therefore, they appear bunched together ahead and spread out behind. Now, sometimes they ask for a diagram to go here. Because they haven't here, we don't need to give one. If you feel like it was going to help you explain this, this is quite a weird, it's difficult to articulate, then do so. Just try to give yourself some space and maybe doing it up in this little bit here if you were desperate to. Okay, but the idea is you just have to describe the fact that each time these waves are being emitted, their emission point has moved slightly because the person's moving forwards all the time. Therefore, the wave front ahead, they start to bunch up. Behind, they appear to have been spread out. What this then means is, because we know sorry. Perhaps we should be more clear here. So we've said, as they move forwards, ahead they appear more bunched together and they appear more spread out behind. This means In front, the wavelength has decreased. Behind, it appears to have increased. Now I am going to just do a little quick diagram up here, just to show my point. Sorry, it's not the most artistic piece in the world, but hopefully you can see that each of these solid circles is the 3 different emission points as the object's moving forwards through those 3 positions. And this is the wavefront each time. In front, they appear more squashed together. What that means is the length or the distance between one maximum to the next, the wavelength, has got much smaller. Whereas at the back, the wavelength, the distance between maxima, has got much bigger. Okay? Sorry, the sun's just come out and there's a big shadow from my window. You have to just deal with that. Behind it appears to have increased because V equals F lambda and V is unchanged, which we've said already in our answer. We've said that the speed of sound is independent of the motion, so the velocity will stay the same. Because the velocity is staying the same, and because the wavelength appears to either increase or decrease, the frequency must do the inverse. So if wavelength goes up, we must decrease our frequency. Whereas if the wavelength decreases, we must have an increase in frequency. So behind it appears, the wavelength appears to have increased. Ahead of the trailer, frequency will increase. Meanwhile, behind will have a decreased frequency, which obviously relates to the sound we hear. As things move away from us, they sound lower pitched, and they're moving towards us, they sound higher pitched. So you know, hopefully, that your frequency should be bigger coming towards you and getting smaller as they move away from you. So that's what your goal should be. If you reach a different conclusion, perhaps you're using the equations slightly incorrectly. For this question, to get excellence, you had to state, first of all, that these first 2 things do not get affected by the motion of the trailer or any motion. And you then had to say and describe why the wavelength both increases and decreases based on being behind or in front of the trailer. And then both of the frequencies is either decreasing or increasing respectively. If you did only 5 or between 3 or 5 of those sorts of points, so 1 point at the top, 2 for the wavelength, 2 for frequency, if you did between 3 and 5 of those points, that was merit. If you only did 2 of those points, these are grouped together, or these 2 wavelength statements and these 2 frequency ones, and that's achieved. For everything as a complete answer, fully correct is E8. If there was one small error or inaccuracy, then it went down to an E7. And that was question 1. Now, question 2 was even more questions about Sam and her violin. Now, we're told that on a hot day, the violin can easily go out of tune. As things get warmer, they start to expand, and because we're talking about strings being a certain length and frequency, if the wood around it expands, the strings change length, therefore change pitch. Sorry, tangent. As a result, Sam has to adjust the tension in the string to keep the G string so that it still vibrates at 196 Hz. The same way you have to keep a piano tuned, guitar tuned, everything like that needs tuning. Describe what happens to the fundamental frequency of the string when the string gets longer and nothing else changes. Okay, now we're told that nothing else changes, and the wave speed equation, v equals f lambda, tells us that if everything stays the same about the violin, it means that our velocity is staying the same. If velocity stays the same, but the string is getting longer, then the wavelength must be getting longer because the literal length of the wave is being made to get bigger. If we have to keep the velocity the same, that means the frequency of the sound decreases, which means they'll hear a lower note. As V remains the same and L increases, so too will the wavelength lambda, therefore f, the frequency, must decrease. Okay, and achieve for saying frequency is decreasing. There's not enough of an explanation, you won't get that achieve mark, you have to have some reasoning as to why. Now, part B. Sam uses a tuning fork that will always vibrate at 196 Hz. She plays the string while sounding the tuning fork and she hears a beat. You're given two things to do. Describe what is meant by a beat first of all, and then explain why beats are heard. So the first thing you're going to do is hopefully a nice sort of definition of what a beat is. Now, beats are a pulsing of the loudness of a sound due to two similarly frequencied waves. Probably isn't the best way of saying that. Due to two waves with a similar frequency interfering. So often this is heard when you're playing stringed instruments. If one of your strings is slightly out of tune and you go to play the same note, you'll hear an audible change in the volume of the sound you're hearing. Okay, so that's what's meant by a beat. We can tick that bit off because we've done it. We've explained what a beat is. And now we have to explain why they've heard. I've sort of got myself started here because the two waves have slightly different frequencies. They go in and out of phase. Okay, now we're just going to say, when do you hear things that are louder? When do you hear the quieter sound? When the waves are in phase, the sound is louder due to constructive interference. Then the same for the opposite. When the waves are out of phase by 180 degrees, the sound is quieter due to destructive interference. Oh, sorry, it wasn't on the page. Sorry, here you go. Same sentence, just the opposite. maybe a good point. If you're making a mistake and write over something but it's still illegible, it's not clear, do scribble it out and just write it again normally. Sorry. So for saying all those points, that's what you need for merit. These last two bits, saying in phase is louder due to constructive and out of phase is quieter due to destructive, is enough for achieve. Or if you just said sort of the definition of a beat, that's also achieved. You do both together, all together, you get a merit. Okay. Now, part C, we are told that Sam hears a beat of 2.1 hertz. Determine the possible frequencies at which the string is vibrating. Now, we're not told this equation, the beat equation, so if this is maybe something to write down in your resource sheet at the very start of the exam in case it comes up, FB, meaning the frequency of the beat, is equal to the magnitude of F1 minus F2. Now, for those that aren't familiar with this symbol, these two vertical lines on a calculator, mine's no good because they're all rubbed off. It's useful just for making an answer positive. All that the absolute value or the magnitude of it means, this button here, is it makes any negative number positive. So if I put -4 into it, it gives me 4. That's all. It's this abs button stands for absolute. Absolute value just means convert any answer into a positive number. Because we cannot have negative frequency, whichever way around your frequency calculation is done, you must get a positive answer. So we use the absolute value. But just to check, it's ABS on your calculator. Mine's half rubbed off, so it doesn't really come up, but it did used to say ABS. Okay. Now, because it can either equal one minus the other or the opposite, because we're getting rid of negatives, it means we have two possible solutions. The fundamental frequency, or the fundamental frequency, same as it was before, is equal to is equal to 196. Now, F1 and F2 equal 196 plus or minus 2.1. Because we have this magnitude, this absolute symbol around it, it means it's either a plus or a minus. Therefore, the two frequencies are going to be 198.1 hertz or 193.9 hertz. So because we're not sure which one was the higher or lower one, we have two possible answers. Okay. You see this absolute sign? It always means, or usually in any problem, that you'll have a plus or minus answer in the end. Okay. In the same way, if you square root a positive number, you don't know if it's going to be positive or negative root. Okay. Now, part 2 of this question, this is quite a long one. She increases the speed of the wave along the string by increasing the tension in the string, and the beat frequency increases. Use this information to determine the frequency at which the string was vibrating before the adjustment. Now, because we're talking about a violin here, if we tighten the string, we have not changed the wave length. The length of the string does not change, but we are told that she's increasing the speed of the wave when she tightens the string. So in our V equals F lambda equation, we're keeping the wavelength the same. We've just been told that the wave speed does increase, which means that the frequency must have got bigger. Okay. Now we're told that the beat frequency increases as she makes this change. So if the beat frequency is increased as the wave frequency is increased, the frequency has got further from the correct frequency. Okay, now if the beats are have a greater frequency, they're happening more per second, as we're making the actual frequency bigger, it means that we must be making the frequency even further, even higher than it was originally. Therefore, it was a higher frequency, which is 198.1. If the frequency of the sound had got lower, the beat frequency had got smaller, it would suggest that we were getting closer to it. Therefore, it was 198.1 hertz. Sorry. Okay. Now we're asked, what must Sam do to get the string to vibrate at 196 hertz? In order to decrease the frequency, it's the opposite of what she did in part 2 here. Because above, she increased the beat frequency by increasing the wave frequency, by increasing the wave speed, by tightening the string, increasing the tension, in order to decrease the frequency and then do the opposite of everything I just said. She should loosen the string or lower the tension in the string. And then again, we can quote the equation and say that as we decrease this, we're keeping the wave length the same, so the frequency will decrease. And that's what I'm saying here. In order to decrease the frequency, she should loosen the string and decrease the wave speed and frequency. Okay? Now, part IV, part 4, state how she will know when the string is vibrating at 196. If she tunes the string correctly, the beat frequency will go to 0, so she will hear no beats. She would hear no beats, just a single 196 hertz tone or sound, whatever word you like using there. Okay, now part D. When Sam plays a frequency of 564 hertz near a wine glass, the wine glass rattles on the shelf. Give an in-depth explanation of this phenomenon by describing the phenomenon and explaining how she might stop the wine glass from vibrating when she plays the violin. Now, if you've got a wine glass just hanging around on a shelf, I'm going to sort of try and draw a topographical, that's a rough diagram. Let's say this is Sam, and therefore this is her badly drawn violin, very badly drawn. And we got a wine glass on the shelf, the rim only. When the sound waves go over across the room through the air and start to collide with the wine glass, the first sound wave will start making the wine glass vibrate a teeny little bit. Now, if the frequency matches the resonant frequency of the wine glass, what happens is every subsequent wavefront essentially makes the wine glass move at precisely the right amount with the right frequency to vibrate further or increase the amplitude of the vibration to the extent that it begins to rattle. Because the air movement starts off very small, but then the actual rattle means there's quite a significant movement. It's this idea of resonance. Okay, so the phenomenon is resonance. If you say that, that's achieved. Okay? This occurs as the frequency of the violin note matches the natural frequency of the wine glass. Okay? What that means is that nearly all, well, a vast majority of the energy in the sound wave is transferred successfully in a constructive way to the wine glass. Therefore, the sound waves transfer energy efficiently to the glass, causing increasing vibrations. Which obviously results in the rattling. Now, in order to stop the rattling, there's a number of ways that you might do this. First of all, if you put some sort of barrier between the violin and the glass, the vibrations may struggle to get through whatever barrier it is, therefore prevent the sound waves ever vibrating the wine glass. You could always put something in the wine glass or add a sort of like rubber or fabricy material underneath the wine glass to effectively damp this whole system. So for the merits, for an achieve answer, it just says give any practical way to stop the rattle. For excellence, you have to have completely explained how the resonance works, as well as how you might stop the vibrations. There's not really a right answer for how to stop the vibrations, but any of the ones I've sort of said would work. To prevent the glass rattling, adding a liquid to the glass would alter its natural frequency, or its resonant frequency, sorry. Because its natural frequencies doesn't change, you can have water. Or rubber layer, or in a different room. I mean, there's a million different ways you could do this, as long as it's somewhat sensible. Yeah. But it's this idea that you want to just stop the sound waves either from matching the wine glasses or from reaching the wine glass. Or this idea of damping, having a layer of rubber underneath just to absorb the excess energy. If you did all of that, that's excellent. If you did just this top bit, that would be merit. With the additional practical element, that's excellence. If you just did this bit, or if you just said this first sentence, it's resonance, that would be achieved. And that's question 2. Okay, question 3, we finally move away from sound and violin. Now we're looking at diffraction glasses. Now at a fair, children are buying rainbow glasses made of diffraction gratings in a cardboard frame. Steve shines a laser pointer through one of the diffraction gratings onto a wall. The laser pointer produces light with a wavelength of 643 nanometers, and we're given the conversion to meters very handily in the question. The light makes a pattern on the wall with a bright red spot at the center and with slightly dimmer red spots either side. So we haven't got a rainbow spectrum, we've just got red light and red maxima. We are told that the wall is 1.43 meters from the grating. The distance from the central bright spot to the second slightly dimmer spot is 1.75 meters. Now note, that's not the second dot that's slightly dimmer, that's the slightly dimmer one, of which this is the second one. And without the diagram, that could have been a bit confusing, I reckon. But it's not meaning this is n equals 0. It doesn't mean n equals 1. It means the distance from n equals 0 to n equals 2. Now, part A is to describe diffraction. Now, this question is just an achieve one, and it's just for saying some idea of what waves do when they come across a narrow gap that's similar to their wavelength. Okay? When waves pass through or propagate through a narrow gap where width is somewhat similar to the wavelength, the wave spreads out. The wave spreads out or bends. The bending is more to do if it's just on one side rather than it being a gap. If it's going around the edge of an object, it's like a radio wave from a radio tower going around the top of a mountain will get slightly bent. That's still diffraction, but the way we're going to consider it is mostly this idea of passing through a gap. So it's achieved just for saying that as it goes through a gap, the wave spreads out. If you don't say a gap, or if you don't say spread out or bending or anything like that, I don't think you get the point. Okay? So diffraction is just when waves pass through a narrow gap, the wave spreads out. Now the mark scheme doesn't actually require this wavelength requirement, but the most diffraction occurs when the wavelength is very similar to the width. So yeah, as long as sky is blue to some degree. Part B. Give an in-depth explanation as to why this pattern is observed by explaining how diffraction and interference cause bright spots and explaining why there are large sections of light, large sections where there is no light between the bright spots. Now, this is an excellent question, so it's quite a substantial answer. We're going to go through it bit by bit. Now, the idea here is this pattern is observed because we've got diffraction happening. Now, if there are multiple slits, as opposed to gaps, which we used up here, we are multiple slits diffracting the wave, then each slit acts as a wave source. Therefore, neighboring waves from neighboring slits will overlap. Okay, so now we've got this idea of the waves actually passing over each other. Now, if you don't say that, it's difficult to explain as to why the interference pattern is observed. So just saying that they overlap is important. Okay, as they do so, the waves interfere. Okay, so now we've set up the general description as to what's happening. Now we can go into the more precise detail. Okay, so we observe, because the question's asking about how they cause bright spots, I'm going to go ahead and explain how we get bright spots. We observe bright spots where neighboring or adjacent waves constructively interfere. But now we're going to get into the why there are sort of dark spots as well. So in that first bit of the sentence, we've explained why there are bright spots, but now we're going to talk about the second one, why there are no light spots to begin with, and then we'll explain why they are big compared to the bright spots. We observe bright spots when neighbouring waves constructively interfere, but this only occurs when the path difference is an integer multiple of wavelength. Now this goes back to that big diagram drawing we did in class of the two adjacent slits and their corresponding waves being separated by that horizontal distance n lambda. Now I'm not going to go through and draw and explain all that again. Refer back to your notes or your SciPad if your drawing's not very good. But it's this idea that we only get maxima, bright spots, when the path difference is an integer multiple of wavelength. That's why in all of these equations, it's always n lambda equals something, n being an integer, lambda being wavelength. An integer multiple of wavelength is any value of n lambda, by definition. Okay, so we observe bright spots where neighbouring waves constructively interfere, but this only occurs when the path difference is an integer multiple of wavelength. And in fact, we could even put n lambda in there, just to highlight that's what that means. Now we need to explain why we get large dark areas and large dark areas. When the path difference doesn't equal n lambda, destructive interference occurs. Okay. So we've got this idea that as soon as we have non-integer multiples of lambda, we get destructive interference. Now, we can use common sense a bit to remember this. If I have 1.01 times something, or times the wavelength, let's say the wave is 3 meters tall, basically it will be the same. However, as soon as I go, let's say to 1.1, I'm getting quite significantly different numbers now. And so, because it's hard to describe, because with these numbers, only very close to the integers will there be destructive interference. And because there's an infinite amount of numbers between two integers, the vast majority of numbers will cause destructive interference. Now, this is quite difficult to explain, and you don't need to go into any crazy mathematical description with it. The idea is just that because we're going to have generally so many different slits, therefore different wave sources, it means that we're going to have way more points where there's destructive interference. Okay, as there are so many slits and inverted commas sources, meaning each slit is acting as a wave source, there is a very high chance that the waves will be out of phase, basically. Will be out of phase, so more destructive interference and dark areas will be observed. So it's difficult to describe this last bit, but essentially you're saying because there are so many waves, the chances of all of those waves all being perfectly in phase to constructively interfere is very small. Therefore, as I've argued the opposite, because it's very unlikely or very likely that the waves will be out of phase, it's much more likely there will be destructive interference, therefore dark areas with very narrow areas of bright spots. Okay, that's the idea for that question there. Now, if you said all of that, that was excellent. The main point being describing how diffraction occurs, so there's overlapping and interfering sources. For bright spots or maxima, talk about the path difference of multiple or integers of wavelength, them being in phase. And then for the description of a wide dark region, the mark scheme just says that you form wide dark regions. So it's not looking for a precise word perfect description. It's looking for just the idea. You've described the idea that there are lots of sources, therefore low likelihood of being in phase or high likelihood of being out of phase. Either one of those is true. Now, if you said any one of those points, basically, that was achieved. If you explained why there are maxima and minima, that's merit. Or if you'd said that you get maxima when there are multiple integer path differences, that's also merit. Okay? So, weird question, but yeah. Okay, now this question, part C, is a little bit savage in the sense that it gives you 2 lines to do to what amounts to, on the mark scheme, about, what's that, 5 or 6 lines of working. So even though they only gave you 2 lines, they were expecting a excellence level calculation here. Now there are 2 steps to it. If you skip one step, or if you misuse the small angle approximation, you're capped out at getting merit, even if you do everything correctly. If you are aware that you cannot use a small angle approximation, but make a mistake in doing so, it looks like you get achieved. If you do everything perfectly, you get excellence. Now, I'm going to include a small diagram here because this question is very... I'd be annoyed if I had to sit this paper and get this question with this amount of space in it. The idea is, we're told at the very start of the question, all this information has been pointless until this question, until this part. We're told that the wall is 1.43 meters from the grating. We're told the distance from the central bright spot to the second one, n equals 2, is 1.75. So, if this is our laser source, then the distance here is 1.43 meters. But the distance to the bright spot is 1.75. And so we have this basic triangle with this angle theta here. Now, even just by eyeballing it, if your diagram's half to scale, which mine isn't really at all, but sort of is, the small angle approximation works for values of theta that are about a degree or less. This is quite obviously not going to be a degree or less, but what we do have, if this is our angle, this is our adjacent side, this is our opposite side. And so we can say that tan theta is equal to the op over the edge, or opposite over adjacent. Therefore, theta is equal to tan minus 1. The opposite side is 1.75 divided by the adjacent 1.43. If we do that, being careful to use your calculator in degrees mode rather than radians, 1.75 divided by 1.43, tan minus 1, gives me 50.746 degrees, which equals 50.75 degrees. Okay, now quite obviously this is not a small angle, and so we cannot use a small angle approximation, which means n lambda equals dx over L cannot be used. This is small angle only, which means theta is less than 1 degree, basically. Whoops. So we have to use SOHCAHTOA to work out our angle. Then we can go and use d sine theta, mind blank, is equal to n lambda. Okay, so now if we want to work out the slit separation, that's our value of d. And so d is equal to n lambda over sine theta, where n is our n is going to be 2 because we're talking about we're talking about the second fraction. That's right. Equals 2 times 6.43 times 10 to the 7, using that wavelength that we had way up at the top, because it was the second maximum that was being asked about. We're going to do 2 times that divided by sine of theta, where theta is 50.75. So now the small angle one only works if this value of theta is very small, because then we can say that sine of 1 degree is about the same as tan of 1 degree. Therefore, 1 degree is about opposite over adjacent. Because this is a significantly bigger angle than is required for that approximation, we have to use tan then sine. If you used the other equation, this one here, and got an answer of like 1.0 something, you still get merit. If you do it this way, the long way, the complete way, you give yourself an answer of 1.66 times 10 to the minus, not 16, minus 6 meters. Okay, and I'm just going to underline my answer here because I've worked around it a lot to make it clear. If you realize you've worked underneath your answer, and then I put it back up here like I have here, either you've got to scribble most of this stuff out, but don't, because it might be useful. It might be a marking point, so don't scribble out any used working. Just make it real crystal clear that that is your answer. Put it in a box, use colors, I don't care. Make it obvious, that's the answer you want them to see. Okay, now, as I said, if you did all that correctly, that is excellent. Crazy for a 2-line question at the end of a page like this. If you made one error in doing this the full way, or if you use the dx over L equation, the small angle equation, you get merit. If you tried to use the small angle equation and made a mistake somewhere along the way, you get achieve. Or if you used 0.875 and tried to work out the first maximum here, so just halved this distance and said that was your first maximum, then that was also achieved. Part D. When the children look at a spot of white light through the glasses, they see that the white spot with spectra on either side, which they describe as rainbows. Give an in-depth explanation of this phenomenon by describing where the spectra will occur, explaining the position of the colours in the spectra, and explaining why they are in those locations. Now, this is only a merit question, and so, well, it doesn't really matter, really. We're going to start with drawing a diagram. Now, I do have coloured pencils, but assuming that we probably won't bring a full set of coloured pencils into our exam, I'm going to answer this with just plain pencil. And it's that thing we've drawn in class a fair bit, but this time, because it is a white light, not a special kind of laser light combined of 3 wavelengths only, we're not going to have 3 lines per maximum, one for red, blue, and green or yellow. We are going to have a complete box for our rainbow, and I'm going to make them more and more spread out as we get further away from the central maximum. See, I'm not really drawing this very carefully, but more or less. Now, only because I know which way around it is, I'm going to put blue on the inside and red on the left. Oh, sorry, the right on the outside, which obviously is mirrored here with blue on the inside, red on the outside. And in our middle one, I'm going to have a little white label. You probably should explain what the letters mean at some point as well. Just to make crystal clear. And again, I'm doing this in white, in pencil, sorry, I didn't say that, so I can rub it out. Now, first of all, describing where the spectra will occur. Okay? Now, we don't need to explain fully as the whole diffraction maxima process because that's been done here. The question isn't asking the same thing twice. You just have to explain, that's why it's not excellence. You just have to explain why what you see occurs. Okay, so what do we see? We will see a spectrum of colors either side of the central maximum. This occurs as different wavelengths are diffracted by differing amounts. And I'm going to quote an equation just to prove a point. N lambda is equal to d sine theta. As my wavelength gets bigger, my angle must get bigger if I keep everything else the same. What that means is colours with a longer wavelength, a larger wavelength, will be diffracted through a greater angle, meaning they get spread further from the central maximum. So even though this is the first maximum, there you go, sorry, you should have drawn that in before. Because this is the first maximum, all light will have its first maximum here. Because blue light has a very short wavelength compared to red light, it gets diffracted least because of this relationship. Small wavelength equals small angle if everything else stays the same. Because red light has a bigger wavelength, it gets a bigger angle of diffraction. Okay? So we are different amounts. So we're going to say the smallest angle of diffraction occurs for blue light as it has the shortest wavelength, therefore the smallest path difference, which is what actually leads to the maxima and minima. Okay, so we said it's got the smallest path difference, therefore it has the smallest angle, and it's all to do with that smallest wavelength. Okay, you can then argue the opposite as well for red, sorry. Because white light is used, all wavelengths are visible as their path differences. Oh, sorry, no one in the screen. Because white light is used, all wavelengths are visible as their path differences increase slightly. And so we see a full spectrum at each maximum. Okay. Always as the path of resistance C full spectrum makes maximum. And then, have we done everything? Have we described where the spectra will occur? No, we've explained the positions of the colours in the spectra. We've said why they are that way, because blue light's the shortest wavelength, therefore the smallest path difference, therefore the smallest angle of diffraction. And if you said the same or the opposite for red, that'd be fine as well. I haven't really explained where the spectra will occur. Okay, I'm going to go back and do that. Yeah, so I need to explain that. Therefore, we see spectra, sorry, that's T, either side of the central maximum with blue nearest the center and red furthest from it. Multiple spectra appear multiple spectra appear multiple spectra appear at each, oh no, one for each maximum. So I've not worded this brilliantly, to be honest, but the idea is now I've described where the spectra will occur. The idea is that they're either side, where the maxima can be calculated, with dark gaps between. That's what I should have said here. With dark regions in between due to non-integer path differences and therefore destructive interference. Okay, so I've done the 3 bullet points, I've got my sketch here, and I have labelled it and made it crystal clear what R and B mean. I would imagine if you forgot to include a key and you've just written the letters, they'd probably forgive you for it and give you the marks. To be safe, always explain what you're doing. If there's any sort of shortening, always make it crystal clear what the actual meaning is. Now, looking at the mark scheme, as I said, this is only a merit question. You get achieve if you said anywhere that there are complete spectra, i.e. it's a full rainbow starting with violet with red on the outside and blue on the inside, red on the outside. If you said in-phaseness occurs due to integer path differences, if you had said that they therefore cause maxima, that's another way to get achieved. Or if you said that they're in phase and produce maxima, that's achieved. For merit, the idea was explaining why we get violet or blue on the inside and red on the outside. And it's this idea of wavelength. This sentence here is the merit one. Sorry, I answered that poorly. I should have given the achieve bits first, then gone on to merit. But did the merit bit here, then went on to the achieve bits. But that was question 3D. And if we check the blank page at the end, that's the paper.